Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today as we celebrate a post-Thanksgiving welcome back to school kind of form here. This is not going to be a practice problems video. I'm actually going to be teaching you something. There will be practice problems involved, but it's more on the lecture-based thing and less on the let's just do some problems. This is going to be on linear functions. We went from arithmetic sequences, which had a linear path, common difference, and now we're going to be using actual linear functions, using y and x again, things like that. Using the word slope, using the word intercept, not so much on the word term and common difference and figure and such. I want to jump right into it here. This first slide you're going to see is very wordsy, and I want to let you know if there's anything that you do want to write down, I will go ahead and recommend that you go ahead and pause this screen at some point. I know there's some points cut off right here. I'll scroll down in a little bit because my face is in the way. So let me just give you the breakdown of what you're looking at, and you're going to see these things again, and I'll show you what this looks like. This is all on linear functions. It's basically a whole chapter of a book, sort of a textbook, if you think about it, or at least half of one, depending on what your textbook would talk about. There's not going to be too much in the form of making equations for graphs or graphing from equations using forms. That'll be probably in the next set of videos that I do, because that's in our next module. But here's what we got. I have color-coded and numbered certain learning targets and success criteria. And they're broken down as follows. The number ones in purple, the learning target and success criterion, are both for just understanding linear functions. And you're going to see these again, so I'm not going to read them out loud right now. The second one down here in blue is for, oh, by the way, there are target words over here on the right side in purple, blue, and green. The second ones down here in blue, number 2, are for using intercepts, okay? And the third one in green right here is for interpreting rate of change and slope. So if you want to pause this video in 3 different sections, I recommend that you do so. I'm going to start with the purple-based stuff first, all the purple stuff, and then we go into blue, and then we go on to green. Okay, so, and these are just random visuals. They don't have anything to do with anything. All right, so I'm just going to go ahead and get started here because this video could be long, depending on what's going to happen. All right, understanding linear functions. By the end of this, we want to be able to recognize a linear function both symbolically and graphically. I'm going to start with symbolically, and by symbolically, I either mean by equation form or by table form. Can we understand symbolically whether or not something's linear? Can we determine it? Graphically comes next, and it's arguably easier. Can you look at a graph and decide whether or not a function's linear? The success criterion here, how will we know that we are successful in what we do? Well, I'll note what's called the degree of the variable, or the variables in each equation. All right, that's what we're going to do first. And or seek a linear appearance in the graph of a function. If this is done by a table, we'll be looking at something as well. It'll make more sense in our definition stuff. Okay, what is a linear function? First of all, you have to know what a function is. That means for every x, there's only one y value. So assume everything's a function unless you see otherwise. We'll see one example of a non-function here, and I'll call it as such. A function is linear if each existing variable in the equation is of degree 1. Of degree 1. What the heck does degree 1 mean? Well, that's what the next bullet point's for. The degree of a variable is determined by its exponent. Even if it's implied, and by implied I mean even if it's not written, we should still know what the exponent is. And I'll show you what that looks like right now. So let's say we have a general equation here like y equals 2x plus 3. And I ask you, is this representative of a linear function or a nonlinear function? The implication here for each variable, the y and the x, is that the exponent is a 1. Y means y to the first power. X also means x to the first power. It's not written, but it is implied. And because it's a 1 in the exponent, that means that these each have degree 1. Degree 1 for y, degree 1 for x. At least for the terms, or at least for the variables, these terms are also of degree 1. The 3's term is called of degree 0. We can ignore that because I talked about the existing variables, not existing terms. So as long as the variables are of degree 1, in the long run, that's really what we're looking for. There is a caveat to this. If this had x and y together like this, technically this is of degree 2 because 1 plus 1 right here. We're not going to see any of those though. So ignore that one there, but yes, this one's linear. in this case right there. And we're going to see some other ones. I just want to give you examples of what does implied mean and what do the degree means. What do the degrees mean? How about this? Y equals 3x squared minus 4. Well, this y to the first power is still of degree 1, but suddenly the x squared term, this is of degree 2. Because it's of degree 2, this function then becomes nonlinear. If I graph this, it actually becomes one of those U-shaped parabolas. So it doesn't make, a line, which is kind of what we're looking for there. Here's another one we're not going to see. And again, this does upset my definition quite a bit. This is of degree 1, this is of degree 1. However, this x isn't specifically just of degree 1 because of it being inside an absolute value. It creates something different. So I know that my definition's spotty. I'm trying to make it as basic as the people that I'm teaching what kinds of equations that we're looking for now. Here's another example of something that you may believe is linear that ends up not being linear. Something like this right here. This y is of degree 1. This x appears to be of degree 1 right here, but the issue is the x is not in the numerator. And there is a way to write this thing in the numerator, but you can't just write it like 5x, because 5 divided by x is not the same thing as 5 times x. These are clearly not equivalent. But there is a way to write it with x in the numerator, and that is if it's to what's called the negative first power. X to the negative first power, like that. Well, this y may be of degree 1, but the x term is of degree negative 1. So these are not both of degree 1, therefore this is also nonlinear. This rational function has a strange curvy thing to it. It's kind of different. I'm not going to graph them, but the point is I can look at an equation and let you know whether it is linear or nonlinear based on the variables being of degree 1 in the numerator, not inside a square root or an absolute value or something like that. The implication, by the way, let me show you square root, for example. The implication says otherwise. When it's not written there, there's a little more to the story. Y equals square root of x. That x may look like it's to the first power, but in the end, if we removed that square root, kind of what we're saying here is it's really x to the 1/2 power. Kind of sweet. You don't have to know that, but I'm making you aware that implications change your knowledge of what's there. So in the numerator for every variable, so this is nonlinear, by the way, in the numerator for every variable of degree 1 implicitly or, explicitly written out, and nothing around it like radical functions or absolute value functions or things like that, not multiplied with each other. Can't multiply that x with y and make it of degree 1. Last thing I wanted to write, something like this, y equals 14. There's no x here, but is every variable that's in here of degree 1? Yes, the y is of degree 1, therefore this is also a linear function. It's also called a constant function, but linear, it also makes a line, so that's the important part. Okay, so let's go ahead and look at some examples. Tell whether each function is linear or not. Y equals 3x squared. Because this is of degree 2, it is a quadratic function, actually. This is nonlinear. No, definitely not linear function. That's one of those parabolas. 7 minus y equals 5x plus 11. Now, despite the fact that I would maybe want to write this in proper form, I'm going to do it a lot more later. Right now, I just want to look at these things and ask, can I look right off the bat and say, is it linear or not? This is of degree 1. This is of degree 1. They're separated, yada, yada. Yes, it's linear. X, degree 1, y, degree 1. Yeah, I could distribute the negative 2, do things like that. This is also linear. So I'm doing it in a point-blank way. I'm really looking at the degree of the variable, and I'm letting you know right then and there, is it linear or not? X plus y equals 10, also linear, all of degree 1 there. That works. You know, I'm going to make these purple just to kind of keep the thing going, whatchamacallit, the theme, the purple theme going. Here's a perfect example of what I said is nonlinear. This is really y equals 2x to the negative first power, interestingly enough. Not of degree 1, it's of degree negative 1. This is nonlinear. It's called a rational function. It looks different. It is a function. And x squared minus x. There is an x of degree 1, and no, these do not combine. This y is of degree 1, but because this is of degree 2, this will dominate precedence as far as what we refer to the degree of the polynomial as. This is a quadratic. This is not linear. Definitely nonlinear. All right, so there we go. Half linear, half nonlinear. That's what it looks like. That's what we're doing. Hopefully I can get through the practice problems kind of faster and make sense of things. All right, another symbolic form of finding out if a function's linear. A function's linear if each Oops, I wrote this wrong. How about if each amount of change per 1 unit interval remains constant? What the heck did I just say? We're going to kind of see this thing again later, but how much is something changing? How do I say this? How much is something changing on y as x just goes up by 1? That's kind of what's being asked here. How much is y changing by each time? Is that change constant per single unit interval as x goes up by 1? So we look at an equation. Complete the tables. Is the change constant for equal intervals? If so, what is the change? What I'm going to do is I'm going to substitute values for x and get values out for y. And actually what I recommend here is get y by itself in your equation. Meaning, like, if I subtract 3x from both sides, and then if I divide both sides by 5, and I get y equals, and this is debatable whether or not you actually want to divide by 5 here, but I'm going to, because you're going to see more equations like this than not down the line. All right, y equals negative 3/5 x plus 4/5. I'm going to substitute values in for x and get values out for y. And for the sake of room and time, let's do it mentally. Plug in 0 for x. Negative 3/5 times 0 is 0. 0 plus 4/5 is 4/5. 1 times negative 3/5 is negative 3/5. Plus 4/5 is 1/5. 2 times negative 3/5 is negative 6/5 plus 4/5 is negative 2/5. Okay, so the question is there a constant rate of change from one value to the next? It's kind of like when we did sequences and asked, is it a common difference? Not kind of. That is what's being asked. Is there a common difference? Am I adding or subtracting the same number over and over? In this case, and I want to use a different color here to make sure I can kind of see it, I'm subtracting 3/5 here, I'm subtracting 3/5 here, and I'm subtracting 3/5 here. Yes, it looks like I'm subtracting the same value each time. Yes, there's a constant that changes by negative 3/5. Therefore, is this linear? Yes, it's linear because it has a constant change. Now, did we already know it was linear? Probably. First power, first power. So we can probably answer the question before looking at the table, but now we're looking at the symbol thing to make sense of it. So, like this next question right here, do we already know if this is linear or nonlinear? Because this is of degree 2, this is quadratic, we already know it's going to be nonlinear. So, constant, there's not going to be a constant. Not when you keep checking over and over. But let's go and see for ourselves. Let's rewrite this to get y by itself. Subtract 4x squared from both sides. And I'm going to go and substitute some of these values. They substituted some for us already. They substituted negative 1 and 0. Now we're going to substitute 1. 1 squared is 1 times negative 4 is negative 4. Plus 4 is 0. 2 squared is 4 times negative 4 is negative 16. Plus 4 is negative 12. So even though you look like, oh, look, I added 4, and then I subtracted 4. Look, it's 4. It's the same thing. Well, no, 1 is plus 4, 1's minus 4. Plus, when you look at this one, now it's going to be minus 12. Clearly a big difference going on here. This is not constant. There is no change to make mention of because it's not constant. So it's not remaining constant in that case, therefore it's not linear, right? That's the idea of the definition. And so symbolically, we can use a table and decide, are we adding or subtracting the same amount? Same thing with sequences, like I said before. But now we're not using that phrase anymore. All right, same thing here. Can we anticipate this thing's going to be linear? I think so. First power, first power. But let's go ahead and write it by itself. Negative 6. Oh, no, it's already by itself. Hang on. Just want to write y equals first. Y equals 6x plus 1. That's the OCD in me. You're good. Let's substitute all the values. Negative 1 times 6 is negative 6. Plus 1 is negative 5. 0 times 6 plus 1 is 1. 6 times 1 plus 1 is 7. 6 times 2 plus 1 is 13. So we're adding 6 each time here. And remember, it's not so much just that we're adding 6. What's the important part? Per 1 unit interval. That means as x goes up by 1 each time, what is y doing? For example, let's say that instead of having 2 here, let's say that instead I had 4. Now, if I substitute 4 into this equation, what was this, number 7? Let's say it's plugged 4 into here. 6 times 4 is 24, plus 1 is 25. I'm adding 6, 6, and 18? It's not constant? Well, no, it's still constant. The difference is, see, this time we're adding 3, and here we're adding 18. So we're adding 18 after 3. That's the same thing as 6 after 1. So you have to think about it per 1 unit interval. What does 18 divided by 3 reduce to? It reduces to 6 over 1. We're going to be doing more fraction reduction like that, I think, a little bit later in this video, probably when we hit the slope stuff. But yeah, it doesn't matter how that's written. The point is, it's still, let me go back, it still does have a per 1 unit interval, a constant rate. Yes, the change is 6. 6 per 1. 6y's per 1x. All right, and finally, graphically, a function is linear if on a graph every point that represents the function lies on a single line. Now, before we do anything else with this, I do want to make sure that you understand, and I think I say it on the next slide, this curve or line, and I think I kind of answered the question by saying curve, is it linear or not? But these graphs right here, they make these curves or lines, but they all represent these individual points on here. So when we say every point that represents the function, these are points on this thing. Don't just say, oh, it's a line, there aren't any points on it. No, every single thing here is a point. Keep that in mind. Don't forget that when you're doing these things here. And we are going to connect the dots when we do these, unless something otherwise calls for a discrete kind of function, like an arithmetic sequence would. All these will be continuous for the most part. Okay, so if it lies on a single line. So these points here, could I make a single line through these points here? The answer is no for number 1. I could make a curve, but not a line. Number 1 is nonlinear. Number 2, however, these points make a single line, therefore it is linear. Okay, so hopefully that's making some sense here. This will be pretty obvious. Just don't make the mistake on something like number 3. Number 3, this is actually called an absolute value function, this V shape. This may have 2 different straight portions to it right here, but not for a single line. It needs to have a single line here. And this does not make a single line. This is not linear. Even though it has 2 straight parts, it needs 1 straight part. It needs to go like that the whole way. This is nonlinear. Number 4, whoopsie. Number 4, straight line, linear. Kind of running out of room. I'll just put yes or no for the next 2. Number 5, straight line, yes, it is linear. If you get higher up in math, you can get someone who's picky and tell you this is actually just called a constant function, not a linear function. But it is making a line. By rule, it's linear. Number 6, it has straight-like portions for the most part, but it does curve. If even for a slight moment, it is nonlinear. This probably is an exponential function. Not that you need to know the name right now. Okay, remember, degree 1 is if it's linear. A function is also linear if on a graph every point that represents the function lies on a single line. So keep in mind when we look at both of these equations here, the reason why I reintroduced this bullet point right here, degree 1, is to make sure that you know that when we graph these 2 things, they actually are lines. It actually is linear. These are of degree 1. These are linear functions. Now, in order for me to graph these, I'm going to start by using tables for these things right here, x and y. And down the line, you're going to learn different ways on how to graph these without a table. You may already know how to do some of those, but for the sake of argument, let's go ahead and practice this. I'm going to do something that's going to be beneficial for myself. Because I'm going to be taking half of numbers, I'd rather not include any odd numbers in my set. I'd rather include just even numbers. And I'm going to do some positive, some negative. -4, -2, 0, 2, and 4. When I substitute these numbers in, I can take half of them and be comfortable with getting integers out. And then I'm going to plot those points. Half of -4 is -2. -2 minus 3 is -5. So there's a point on my graph that is -4, comma, -5 right here. Okay. Substitute -2. Half of -2 is -1. Minus 3 is -4. So -2, comma, -4 is another point on this graph. Half of 0 is 0. Minus 3 is -3. we plot right there. That's not the best plotting. Not the best plotsmanship. That is even worse. All right, half of 2 is 1, minus 3 is negative 2. And that's 2, negative 2. And half of 4 is 2, minus 3 is negative 1. So it looks like I stayed negative with the points that I chose. And if I draw a straight line through there, I'm going to use my line tool. If I draw a straight line through there, then you'll kind of get that confirmation that this thing has been, and will be linear throughout that. Now I am plotting the points. This is not a sequence. This is something that states that I could have plotted other points in between, and they all would have satisfied some particular solution on my line. All of these would have been valid. And, you know, it's just important to make that note that there's more than these points I could have chosen. I could have chosen 1 and negative 7 and 1,000. That's why I draw the line to state that not that it is linear, or not just that it's linear, but also that any of these points matter. This is continuous. This can be chosen that way. So there's my linear function. An important thing of note that you can probably see is that these things always went up by 1 each time. Now, is that change going to be 1? Keep in mind, this is supposed to be per unit interval. I'm going to go back to this idea. Where was it? Per 1 unit interval. That means as x goes up by 1, these x's didn't go up by 1. They went up by 2. But they still went up a constant amount, which allowed us to say that as long as these went up constant, then it's good. But these y's went up 1 every time the x's went up by 2. That means that the x's only went up by 1. The y's would actually just go up by 1/2. So the actual change is 1/2 per 1 unit interval. Kind of something I'll talk about later. But it is constant. There's a nice confirmation. Okay, so I went ahead and just, I had a quick pause. I looked at this problem, and it had an 8 before. I didn't like the appearance of it for what we're trying to do with these problems. I think later down the line, when we look at the intercept stuff, I think that comes up next. I wouldn't mind having the 8 there, but for this particular problem, I want to make it a little simpler for what we're doing. I'm going to change it to a 9. It has to do with getting y by itself, because the whole goal right now is to treat y as a dependent variable for the sake of function practicality. And in getting y by itself, let's see, 3y equals negative 2x plus 9, subtracting the 2x over, and then dividing both sides by, 3. In getting y by itself, I divide everything here by 3. So I get negative 2 thirds x plus 3. See, if I had this as 8, I'm dividing 8 by 3, and I don't want to deal with the intercept stuff right now like that. So, okay, this is fine. Or with fractions, I mean. So this is fine right here. I'm going to go ahead and substitute values. I'm going to create another table. I'm going to substitute values for x that when I take 2/3 of them, they become integers again. So numbers that are divisible by 3. So negative, let's see. Let me think about numbers that, first of all, will fit on this graph. If I choose, is that okay? Yeah, that's fine. All right, so we'll choose negative 6, negative 3, 0, 3, and 6. I think these should fit. Okay, so negative 6. Negative 6 times negative 2/3 will give me a positive value in the end. 2/3 of 6 is 4. So 4 plus 3 is 7. I think that fits. So negative 6 comma 7 is way up here. Negative 3 times negative 2/3, positive. 2/3 of 3 is 2, plus 3 is 5. So that's negative 3 comma 5 right here. 0, 2/3 of 0 is 0, plus 3 is 3. Whoops, 3. 2/3 of 3, again, is 2, but now it's negative, because this is negative, this is positive. So negative 2 plus 3 is positive 1. So positive 3, positive 1. And then finally substitute 6. Negative 2/3 of positive 6 is negative 4. Plus 3 is negative 1. So 6 comma negative 1. So there's this graph right here. And again, connecting the dots with a nice straight line, like so, and there becomes that function as well. We anticipated these to be linear. They are linear. That's understanding linear functions, I think, in a nutshell. I think there's one more set of things that I have that I want to mention here, but that is drawing graphs of them, if you have them. Okay, the last bit here has to do with the word solution. Less about the actual, who cares if it's linear? Honestly, who cares if these are linear or not? That point does not matter here. Any ordered pair that makes the linear, or any equation really, but because we're doing linear, any ordered pair that makes the equation true is called a solution of that equation in two variables. So in a linear equation, if I have two variables here, x, y, and I have an ordered pair, they're asking us, is this ordered pair a solution to this linear equation? What they're asking you is, if I drew this line, if I made the graph that drew this line, would this point be on that line? Okay, if I went backwards for a second, so I can make this more conventional, because I'm not going to graph them, I'm going to do it mathematically. If I asked you, is the point -2, 6 a solution to this equation? You can look at the graph. Is -2, 6 a solution to the equation? Is the point on this line? The answer is no, the point's not on the line. But is 3, 1 a solution to the equation? Yes, because the point is on the line. So that's what it means graphically if it's a solution to it. What it means mathematically, or symbolically, if you will, is we need to make the equation true. What makes the equation true? The left side equaling the right side. So is it true that 9, 3 is a solution to this equation? Is the point on the graph, or better yet, when I substitute 9 and 3 in for x and y, do I get a true statement? Let's check it out. 9 times 9 is 81. 4 times 3 is 12. And 81 plus 12 is indeed 93. Yes, this point is a solution to the equation. That means if I made this graph, this point would be on the line. Okay. And by the way, again, this doesn't have to be linear equations. This could have been a U-shaped quadratic equation, but because we're talking about linear equations, I don't say point on the line, but I could have done the same kinds of tests for those things. That's what I'm trying to say. All right, same thing here. 5x plus 8y equals -32. -6, 0. Substitute -6 for x. Substitute 0 for y. -30 plus 0 equals -32. Doesn't look like that one's going to work out. -30 does not equal -32. Nope. No, that point is not on that line. Therefore, it is not a solution to the equation. And the very last one here, y equals 7/8 x plus 9. Be careful what you substitute for here. The left 32 right here doesn't plug into this y right here. 32 is for x, okay? 28 is for y. So 28 for y, 7/8 of 32 plus 9. And I implore you to do this without a calculator. Remember, 32 may be multiplying by 7, but just the same, it's also dividing by 8. So this is going to be a lot faster if I do this mentally. 32 divided by 8, which is 4, times 7, which is 28. So I get 28 equals 28 plus 9. That doesn't sound right. So 28 equals 37. I don't think so. Therefore, no, this is not a solution to the equation as well. That point is not on that line. And yes, these are all linear equations, all of first degree, all that jazz. All right. So that's all right. So that wraps up the understanding linear function stuff. So can you recognize a linear function both symbolically and graphically? By stating that you will note the degree of the variable in each equation. You can look at the table and look at constant change, look at the linear appearance of a graph, and you also know how to do solutions. I did more things than just those things, but that's really the big learning target. All right. So you can go ahead and press pause at that point if you feel like, or quit out if you feel like that's all that you need to know for your stuff for now. The next thing I'm going to do is using intercepts. So if you want to keep on going forward, let's keep on going forward. All right, using intercepts, learning target. This is nice and blue. I can graph linear functions and show and interpret intercepts. So graph linear functions, we just did some graphing linear functions. I'm going to show you a different way to graph them now, though, using two very specific critical points called intercepts. And you can show where they are, and you can interpret what they mean in context if necessary. Success criterion, you can find the x and y intercepts of a function in any sort of way, either by graph or by equation, and connect the points accordingly. That's how we're going to be graphing them, connecting the points and the intercepts, and you can then provide context for said points if necessary. The x-intercept and y-intercept are the target words. They'll be defined for you right now. What are intercepts? Intercepts are points that lie on the axes of a graph. You can see right here what's in green and in red. These are considered intercepts. These are the x and y axes. The x-intercepts lie on the x-axis, and the y-intercepts lie on the y-axis. In this case, for a linear equation, there can only be as many as one x-intercept and one y-intercept. For any function, there can only be as many as one y-intercept. But you could have, this doesn't apply to us, but you could have a quadratic equation and boom, 2 x-intercepts, 1 y, or something like that. You could have a quadratic where it doesn't hit the x-axis at all, or a straight line doesn't hit the x-axis at all. But anyway, where it crosses the axes or where you see the intercepts. This A is just a generic letter used to represent what the actual x-intercept value is. The actual value, like the x-intercept is A, and the y-intercept here is B. And even though you won't see this too often for any particular reason, get used to seeing this when we use what's called slope-intercept form. That won't be today. But B right there. Now what's important here, before I get to this therefore part, what's important is noting these actual coordinate pairs. This is A, 0 for the x-intercept and 0, B for the y-intercept. And like I just stated before, the x-intercept value is actually the A and the y-intercept value is actually the B. So how can I determine what the A or B are if I have just an equation, or if I want to see something more to it? It's not just where it crosses an axis. The x-intercept is the value of x when y equals 0. Look at the coordinate pair, A, 0. When it crosses the x-axis, y is always 0. Always, 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 always. Therefore, when y equals 0, that's where we'll find our x-intercept. And hey, when x equals 0, we can find our y-intercept right here. When x is 0, the y value is going to be that whatever the b value is right there. Now, why does that matter? Because we're not always going to see things as graphs. This is a very generic form. I don't have an equation for you here. But here I have two equations, and I'm not going to graph them right now. We're going to look at the equations and say, find the x and y intercepts of the graph of the linear equations. That doesn't mean graph it. That means that if they were graphed, where would they land? But I'm not going to graph them. 2x plus 3y equals 12. I want to know what the x and y intercepts are. I'm going to do this in black just because there's a little too much blue. Let's find the x-intercept first. To find the x-intercept, what I'm going to do, once again, the x-intercept is the value of x when y equals 0. I am going to set 0 for y. 2x plus 3 times 0 equals 12. Here's the cool part, and this is the only time I'm going to actually write this 0 here. Here's the cool part. 3 times 0 is 0. And what does it mean when you add something to 0? It simply goes away. So I could have skirted by. I could have ignored writing either of these two steps. When I substitute 0 for y, that term, this is standard form. In this form right here, there's just that y. This term just goes away. And it just says 2x equals 12. That's very easy for me to use to solve. Divide both sides by 2, we get x equals 6. So the x-intercept is 6. Therefore, the coordinate pair is 6, 0. I'm more fascinated in looking at the coordinate pair than just the intercept value. I know that they're both equivalent. They're one the same. But I want to keep reinforcing the fact that the x-intercept is the value of x and y equals 0. Some people seem to forget that. We need two numbers for a point. All right, we always need two numbers for a point. All right, I got to erase the x-intercept information, though, right here to get the y-intercept because there's just not much room. The y-intercept here, I got to set x equal to 0. I'm very simply setting x equal to 0. This goes away. See if you can make sense of that. 2 times 0 is 0. It's gone. So my equation just says 3y equals 12. So for my y-intercept, I divide both sides by 3. What do I get? Y equals, 4. So there's a point on my graph also that is 0, 4. That is my x-intercept and my y-intercept. Sorry for the sluggish writing. X-intercept and y-intercept. Technically, again, yes, the x-intercept is 6 and the y-intercept is 4. The coordinate pairs where they exist, though, are on 6, 0 and 0, 4. And I could plot those points on a graph if I wanted to. It's very straightforward to do. Simplest math you can do. Simple, single division when they're written in this standard form. Let's do it again. Super neat, super fast. X-intercept, y-intercept. I'm going to go ahead and see if we can do this mentally this time. Just by covering this. Set y equal to 0 for the x-intercept. 3x equals 2. Divide both sides by 3. X equals 2/3. So I get 2/3 comma 0 for my x-intercept. Neat, huh? Y-intercept. Set x equal to 0. Make sure this is still negative, though. Negative 6y equals 2. So y equals 2 over negative 6. Now that reduces, let me just write that. 2 over negative 6, that reduces to negative 1/3. Right? It's a negative number. 2 over 6 reduces to 1 over 3. So that's 0 comma negative 1/3, like so. Those are my x and y intercepts. Simple calculation, kind of weird numbers, but that's okay. Simple division, we got it taken care of. And that's how you find x and y intercepts. You set the other value equal to 0. That's it. And by the way, this isn't just for linear equations. This is for any kind of equation that you have. Okay, so let's go ahead and graph them using only the intercepts. Now, what I just said before here still holds true. All this stuff right here. Intercepts are points that lie on the axes on the graph in these parts. It says graph using only the intercepts. Gladly. Gladly. I have my x and y axis here. Remember what I did in the previous equations in purple, where I got y by itself and I plugged in values for x and got values out for y, yada, and connected the dots. Remember, to make a line, you only need 2 points, right? There's no way, if I make these 2 points right here, there is no other line that can go through these two other than the line that I draw. That's not clearly perfect. That's the only line that can go through these 2 points. There's no other line that I can make out of these two, if you know what I mean. Or I can't make the line anywhere else other than through those 2 points. So if I get my 2 intercepts for my graphs, I can plot those and just draw the line through those. Simple as that. Especially when I'm not in that other form where y is by itself. I'm in this standard form. I'm in this form right here where x and y are together, and I might not be able to get a good fraction out. You know what I mean? So let's just find the x and y intercepts. Let's find the x-intercept for the equation. I'm going to use purple this time, or blue. I'm going to use the, find the x-intercept and y-intercept for the left equation. X-intercept, set y equal to 0. 5x equals 30. X equals 6. Divide both sides by 5. So the x-intercept is 6 comma 0. I'm going to go and plot that point. Assume these go up by 1. Hopefully you can see those little points right there. 6 comma 0 is right there. Y-intercept. This time I'm going to go ahead and set x equal to 0. 3y equals 30. Divide by 3. Y equals 10. So when x is 0, y is 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Then go up right there. These 2 points make a line. Now, if you had a ruler, that would be fabulous. I'm going to go ahead and kind of use my line tool and draw that line right there. Boom. 2 points make a line. That is all that I need. And that's enough. I've made my line using my intercepts, and it was simple. All of it was mental math for me to write those 2 points for this graph, and I did it. Okay, that's all you need. It's very quick. Let's do it again in quick fashion. X-intercept, set y equal to 0. Goes away. Negative 2x equals 18. Divide both sides by negative 2. X equals negative 9. Negative 9 comma 0. It looks like 10 was 2 away from the side there, so I think 9 is going to be over here. Negative 9. And then find the y-intercept by setting x. I love to be able to just do that. The y-intercept, set x equal to 0 right here. 6y equals 18, therefore y equals 3. So when x is 0, y equals 3. 0 comma 3 is right there. 2 points make a line. Let's go ahead and make that line for ourselves. And boom, there is that line. Very fast. Very little computation. And the computation was so easy. A simple division. It's quite basic when you have this form and you have that opportunity. Use it to your advantage. A line can be drawn through as little as only 2 points. That's awesome. You need at least 2. All right. Okay, interpreting intercepts here. I have a biggish word problem. There's not too much to it, but I have a biggish word problem. We're going to break this down a little, talk about it. All right, again, x-intercepts value of x and y equals 0, y-intercepts value of y when x equals 0. Great. Interpreting an intercept means describing its quantity with proper units at the same instance that the other quantity is 0. What that means, because there's going to be something at the end where it says interpret the intercepts. What it means is state what those points mean in context of the problem. By context, we mean what is the x-axis representing? What is the y-axis representing? And how do we state something with it? You'll see what I mean with this problem. It's going to make total sense. I could even give other examples with this thing internally. You'll see what I mean. A football team has an away game and the bus breaks down. The coaches decide to drive the players to the game in cars and vans. 4 players can ride in each car and 6 players can ride in each van. There are 48 players on the team. The equation 4x plus 6y equals 48 models this situation where x is the number of cars and y is the number of vans. Graph the equation, interpret the intercepts. Okay, they give you some information here so you know what you're looking at. They give you an equation to help model it and give you peace of mind for ease of use. 4x plus 6y equals 48. Notice that everything here has to do with number of people. Number of people. There are 48 players total. 4 does not mean 4, but see, x is the number of cars. 4 doesn't mean 4 cars. X means number of cars. 4 means number of players per car. So 4 players per car times number of cars means how many players are all driving cars and how many players here are all riding in vans. Right there. We're not solving this. We're graphing the different possible ways that you can make this thing, assuming that you have enough cars and vans to make this thing happen. Let's do it by graphing the intercepts, though. Okay. Theoretically, this should be what's called a discrete function because you can't have an integer, you can't have a decimal number of cars or vans. It has to be on an integer. But I will draw the line and I'll show you what points are very important here. Let's find the x and y intercepts. So x-intercept, set y equal to 0. 4x equals 48, divide by 4, you get x equals 12. So 12 comma 0 is a point on this graph. I think it's right at the end right here. And then the y-intercept, set x equal to 0 right here. 6y equals 48, divide by 6, y equals 8. So when x is 0, y is 8. Keep that in mind. 0 comma 8 is right here. Okay, again, 12, 0, 0, 8. I'm going to graph this. Now, theoretically, this thing shouldn't be, again, it shouldn't be a line on its own, but it also shouldn't have arrows because we can't have negative cars or vans. So I'm really just connecting this in the first quadrant. See, in context, it all matters to make sure that you're understanding your scenario. Let's make that as straight as possible. It's important that I do it this time. Make it kind of hollow looking, though. All right, here's what we're looking at. X represents the, what was it? Number of cars. Number of cars. And Y represents the number of vans. Now, they ask us to interpret the intercepts. We just graphed this. They said interpret the intercepts. What do these two intercepts mean? And I don't have enough room to write this unless I guess I can erase this stuff. So I'm going to type this stuff out for you and kind of let you know what the heck we just interpreted. Look at the points in terms of their X and Y in terms of context here. For 0, 8, X is number of cars, 0 cars. Y is number of vans, 8 vans. That means that all 48 players for the y-intercept, the interpretation is that you can take 48 players in 8 vans, meaning no cars. No cars, you can take all 48 players in 8 vans. The x-intercept, however, is a different story. The x-intercept states you take no vans and you take how many cars? 12. Take 12 cars, or you can take 48 players in 12 cars, meaning no vans. That's what the intercepts mean, and that's what I meant when I said describing the quantity, the number with proper units, players, cars, things like that, at the same instance that the other quantity is 0. See, when there are 0 cars, that means there are 8 vans that need to be taken. When there are 0 vans, that means there are 12 cars that need to be taken. So that's what I mean by interpreting the intercepts. And you can do this for any point, but the intercept is going to be one that is used quite often, not even for us to describe, but for a problem to describe so that we can create the scenario for them. Now, that's not the only thing you could do. You could do a combination. You could do a combination of a certain number of vans and cars and still take all 48 people. Is that possible? Look at these points where it's crossing right through an integer value like this one and this one and this one. These are ideal values to optimize your driving situation when it comes to how many cars and vans you can take. Here, this is saying if I take 3 cars and 6 vans, I can fit all 48 people. You can try and do the math, see if it works. It will. By substituting 4 for, where's the equation? 3 for X and 6 for Y, you'll get 48. Or you can do 6 cars and 4 vans. Or you could do, not 8, you can do 9 cars and 2 vans. Any of these 5 solutions, remember that word, any of these 5 solutions would ideally work out the scenario. In terms of interpreting the intercepts, though, it's literally just these parts here. Take the 48 players in 8 vans, all 8 vans, no cars, or all 12 cars, no vans, or you can do a mix and match of cars and vans like that. All right, but that's what we're looking at there. That's what it means. I think this is the end of the intercept stuff right here, so hopefully that was pretty fast and decent. I'm at about 45 minutes through. We're going to go ahead and move on to interpreting rate of change and slope. So if you feel that you've been fine sitting through this, remember, there's like a chapter's worth of stuff with all the different problems that I have. Not really. It's like 3 sections. But hopefully it's feeling okay here. All right. A lot of information on this one. It should go kind of fast-esque. Learning target here is I can calculate and interpret the slope of a linear function given 2 points. The learning target word here is slope, and I'll define it for you very soon. What is the success criterion? How will we know that we've done it right? We'll find the rate of change in both y and x of 2 points via subtraction and division. A lot of stuff there. And when appropriate, we'll provide context for said rate of change to describe that slope. So just like we just interpreted intercepts, now we'll be interpreting slopes. So like in context, like using the values to state what's going on. Okay, and I have some information here that I'll run into when it's pertinent for what we're doing. All right, what is slope? Let me drink some water here. Why don't you read it first? Okay. The slope of a line is determined by its rates of change in y and x. Rates of change in y and x. Keep in mind that we're not talking about actual points anymore. We're talking about how far apart 2 points are. Like if I have this point and this point right here, I want to figure out how much I've changed in x and in y. I'm not going to I'm not going to do it diagonally. We're not going to do that distance. We're going to do x and y distances here and say how much did I go over to the right? How much did I go up? Things like that. Because all that stuff clearly does matter. This goes back to the idea. Remember way back when I talked about, I probably erased the problem. I think it was this problem here. I talked about this and I said how y wasn't just actually going up by 1 because x was still going up by 2. There's something to that we have to make sense of here. Now, there are these words here, rise and fall, when we talk about y. Remember, y goes up and down. So imagine that up means rise and down means fall. Okay, so changing in y means rising and falling, and changing in x means running. And here's a little tidbit here that I want to talk about. See, positive slopes rise and negative slopes fall. So when we go up, we're rising. When we go down, we're falling. However, we're keeping in mind one little nugget. Because rise and fall are easily recognizable as up and down, rise is up, fall is down, it's harder to talk about whether run means go to the right or to the left. So if I say run, I mean to the right. Run is to the right. By default, the word run is assumed to go right, unless otherwise specifically stated. If you hear me say run to the left, obviously we're going to the left. But I want you to think about it more like a timeline. Think about if you have some sort of timeline here, and we say, as time goes by on a timeline, here's the 1800s, and here's the 1900s, and here's the 2000s, and things like that. We think of time going by as time going this way. All right, so think of it like that. As time goes by, what's happening? Are we rising or falling? That's why I said positive slopes rise while negative slopes fall. We assume that run is to the right. Okay, and that's important. because look at this line right here. I want you guys to look at this line right here. Is this line going up? Is this line rising? Yeah, look, see, it's going up. But someone could argue, no, look, it's going down. See that? It's going down. Well, no, but see, it's running to the left when it's going down. We want to say, as it's going to the right, what's happening? Oh, it's going up. So this one is rising. This one has what's called a positive slope. Okay, so let's talk about that. Slopes that rise or fall more per single unit of run are steeper. What I mean by that is, let's say that two things run the same amount. Something runs here, something runs here. They're running the same amount. And one rises this much, whereas one rises just this much. Which one has the steeper slope? The one that rose a little bit for that same unit of run, or the one that rose a lot? Well, the one that rose a lot per the same amount of run is a steeper slope. That one's a steeper slope than that one is. Okay? So steeper slopes have more rise to their respective run. Lines without any sort of rise have what's called a zero slope. So if I only run and do not rise, and my line just goes flat like that, that is a zero slope. Lines without run have what's called an undefined slope. So if it's all rise, no run, it's undefined. I'm going to dive into that a little bit later as far as how we can know that for sure down the road. So let's look at these right here. Here's an example of what's called a steep positive slope. It's going very sharply upward. Doesn't matter if it goes upwards or downwards, it's still steep. Positive slope because it's going upwards as we run to the right. Here's a shallow positive slope. I don't really use the word shallow very much, but if you're not steep, you're shallow. I don't know. I guess it's deep and shallow. Not the right word, but that's okay. Not very steep, but it's still a positive slope. Here's a zero slope. By the way, it doesn't matter what my intercept is. My intercept could be negative, positive, but the slope is positive. Is it trending upwards? The slope is positive. Here's a zero slope right here. Doesn't matter if the intercept is positive or negative. Zero slope, all run, no rise. Shallow negative slope. Now we're going downward. As we run to the right, it is falling. As we run to the right, it is falling. A steep negative slope, and then what's called an undefined slope right here. An undefined slope is an example of a line that is not a function. For this x, I have multiple y's. This is not a function. Good to know, right? It's important to note that there are some non-function equations. Oh, that game's over right there. Oh, that's ooh, Chargers almost came back. That was a close one. All right, so that's the information. If you need to pause the screen, go ahead. I'm going to move on and look at some examples here. Not just yet. There's a little more to talk about. Slope equals m. We're not going to use this letter right now, but m is the parameter, is the variable, is the letter that is used in equations to represent slope. We are not going to be using it in this time right now. I'm just letting you know right now, if you see m, it's for slope. It's all about your rise over your run. Sometimes you fall instead of rise. Think of like negative rise. How much do you change in y versus how much do you change in x? Well, say you had 2 points here. We have some xy point right here, and we have another xy point right here. I want to know how far I went in the x direction, how far did I run, and how far did I rise. If I figure that out, and if I do that division, remember, there is a fraction to this thing. I stated it back over, I don't know where, oh, it's right up here. Division. Rate of change in y and x is all about division. If I divide how much I change in y with how much I change in x, I will create my slope value. I will create my rate of change. Okay? Now, how's it calculated? It's used with kind of a certain formula here. This y2 minus y1 over x2 minus x1. Now, note, that does not say y squared. That means a specific y value like this one right here. I take this y and I subtract this y right here, and I get the distance between my two y values. My y2 minus y1 actually is right there. It's that distance right here. That's how far they go. Think about if this y was 7 and if this y was 1. What's the distance between 1? How much do I have to go from 1 to 7? I do 7 minus 1 to figure it out. That distance is 6. See, that's how the subtraction works. See, distance means difference. In order to find the distance between two things, I subtract them to determine that. x2 minus x1 is going to be my distance from my x values. x2 minus x1 exists right there. and that's the distance between my x values. When I find the distance between my y values and divide it by the distance between my x values, the changes in them, I have created a slope value. Excuse me, I've created a slope value. Now, it doesn't matter if the x was positive or negative, or if the y was positive or negative, and you'll kind of see examples when I do them. You still subtract them, but sometimes when you subtract a negative number, it becomes addition. But by default, think of it as subtraction, substitute it as subtraction, and you'll be set. You're going to see me sometimes not even use the actual formula, so to speak, to do this. I sometimes just do kind of counting. You know, I make more sense. I know the distance between 1 and 7 without having to actually write 7 minus 1. You know, I can just, oh, it's 6. So, or you can count it out. So there are multiple ways you can do these problems, and we're going to look at some right now. We know there's a lot of information. Let's look at these. Find the slope of each line. Now, you are given 2 points on the line here. We are not looking for the y-intercepts. They're not asking for that. We just need to know what the slope is. I need to know from this point 0, negative 3 to this point 5, 3, how much does I rise? How much do I rise? How much do I run? And I will divide my rise by my run. Change in y divided by change in x. Now, there are 2 ways I can do this. They both get me to the same scenario. Let's say that my x1, y1 is my 0 and negative 3, and my x2, y2 is 5 and 3. Let's try this y2 minus y1 over x2 minus x1. Let's do y2, my slope is y2 minus, here's y1, it's negative 3. And when you substitute, you use parentheses, right? Subtract a negative 3, divided by x2, which is 5, minus x1, which is 0. Clearly, I didn't use parentheses here, but I didn't have doubt for those that I didn't have to. So my slope, 3 minus negative 3 is 3 plus 3, right? And this is divided by 5. So this equals 6 divided by 5. That is the slope of this line. That is the rate of change. Every time y rises up 6, x runs over 5. Okay? That's what that slope means. That's what it's telling you. It says that for every 6 of these, there are 5 of these. Okay? That's one way I can do this problem here. Now, before I do the other way, I want to answer the question that a lot of people might have here. Does it matter what I choose to be x2, y2, and x1, y1 for my points? Does it matter which ones are x2, y2, and x1, y1? No, as long as x1 goes with y1 and as long as x2 goes with y2. So for example, let me redo this problem with the same calculations, but I'm going to trade away x1, y1 is going to go over here, and x2, y2 is going to go down here. If I use my y2 minus y1 over x2 minus x1, if I put negative 3 first, negative 3 minus positive 3 divided by 0 minus 5, I'm going to get negative 6 over negative 5. Now, a negative divided by negative is a positive. That still gets me 6 over 5. My answer didn't change. Now, you'll get an incorrect answer if you accidentally do, say, 3 minus negative 3, and then I do 0 minus 5. I can't do y2 minus y1 over x1 minus x2. If I go from one point to the other, I got to go from that same one point to the other for x's. So it doesn't matter which one you choose to be your x1, y1, x2, y2. You do have to make sure, however, that you do, I don't want to erase all that. You do have to make sure, however, that you do go in the same direction when you subtract them. Okay, so it doesn't matter. Here's another way you can do this problem. When we subtracted, we found the distance. How else can you find the distance? If you have a graph, you can kind of count. You can ask yourself, how much do we go from negative 3 to 3? That's what I'm asking. Now, this is harder to count because these increments don't go by ones, they go by twos. But how much from negative 3 to 3? Well, it takes 3 to get to 0, and then 3 to get to 3. That's a total of 6. You rose 6. How much from 0 to 5? How much do I run from 0 to 5? Well, that's 5. 6 divided by 5. It's all about change in y divided by change in x. What's the distance from one to the other? That's my preferred way. It depends on what you have, though. If you don't have the graph, you could draw it, and I'll show you examples of those. When in doubt, draw it out. That's one of my other things there. What was I saying with that? You can draw it. The times that I don't like using it, when the numbers are huge. What if I have to find between the points negative 24, 172, and 920, like, you know what I mean? I'm not going to count that or figure, I'm going to subtract those ones, okay? That's what I'm going to do. I also don't like to do it when there are decimals or fractions or something involved with that. I'd much rather just subtract, save myself the hassle. But if they're close enough numbers, and it's drawn, I'm probably just going to count it. It's probably just a lot easier to say, what's that distance? Oh, it's 4. It's a lot easier to do that way. The one thing you got to be careful of when you're counting, though, is understanding your directions. Why is this a positive 6? Because from this point to this point, I rose. And then from this point to this point, I ran. By running, I mean run to the right. Positive 6, positive 5. Let's do this next example here. In this example, I'm going to do the counting one first. I'm going to go ahead and go here and here. How much do I rise and run? Well, the thing is, as I run to the right, how much do I run from negative 3 to negative 2? I just ran 1, positive 1 to the right. So when I do my division and my slope, I run 1 to the right, change in x is 1. But here, I'm not rising on y. If I'm going from this point to this point, I am falling. Therefore, from 2 to negative 3, the number's not just a 5, I have fallen 5, therefore it is a negative 5. So I have fallen 5 as I have ran 1 to the right, therefore my slope is negative 5 over 1. And if you just reduce that, negative 5 divided by 1 is just negative 5. So I could just write slope is negative 5. And that could be my answer. And it is my answer. That's all. I will, however, do the actual calculation so you can see this one more time and confirm why was this a negative 5. And again, this goes back to your question, which points do I choose to do? Which points do I choose to use when it comes to, how do I say it? Counting my rise and run. Well, run is assumed to go right. My personal go-to, choose the point on the, go from left to right. Choose the point on the left first and go to the right. That way you know if I rise is positive, if I run it's negative. Or excuse me, if I rise is positive, if I fall it's negative. My run will always be positive. But you could go this way. I could go left. See, I could go up and to the left. But now I'm rising 5 and I'm running 1 to the left. That makes the 1 a negative. The 5 is now positive and the 1 is now negative. Does that change my answer? No, it's still a negative 5. But people will forget that you're running to the left. See, that's why, just make run be to the right and it's no problem here. You may think I'm overcomplicating it by giving you the suggestion how to do it. I just say be careful in how you use it. But it's very powerful. It's a nice tool. All right, here's the alternative. y2 minus y1 over x2 minus x1. I'm going to go ahead and make my x1, y1, x2, y2. So y2 minus y1 over, what I choose, negative 3, x2 minus x1. Notice minus the negative. That's going to be addition. Because I'm running out of room, let's see if we can do that pretty fast. Negative 3 minus 2 is negative 5. This is negative 2 plus 3. That's positive 1. And we're back to where we were right here. That becomes negative 5 as our solution. All right, so we found the slope of those lines right there, and they were drawn for us, and we could use those to make it happen. We used the formula. I also gave you the whole, use the drawing to make sense of it. And there you go. By the way, this was an improper fraction. Leave it as an improper fraction. The only thing I'll ask you to do sometimes is reduce your fraction when you have to. So we'll see if the next problems do that. Excuse me. Okay, find the slope of each line passing through the given points. Describe the slope as positive, negative, 0, or undefined. Keeping in mind, positive slope means a positive number, negative slope is negative, and things like that. 0 slope means flat, undefined means like that. Okay, so I'm going to start with the old y2 minus y1 biz right here. x1, y1, x2, y2. Let's go ahead and do that. Slope for this problem is y2 minus y1 over x2 minus x1. And when it comes to these, look, I like to make my numbers positive as much as possible. If both remain positive, that's even better. I get 5 over 5, which is just 1. So there's my slope. It's positive. There's my answer. I'm done. Now, I will consider looking at the alternative route to this. I'm going to draw it over here, and I'll erase all this later. But I could draw these. Now you're saying, what, are you nuts? This was fast. This is fine. Yeah, it was. It was. Drawing will be too. Look, when I draw this thing, I'm not going to do this. 1, 2, 3, 4, 5, 6, 7, 8. No, I'm not going to count this out. I'm going to rough it out. The one thing that drawing does help for here, the one thing it really does help for here is it avoids the mistakes of not subtracting the wrong way, because you can tell if your slope's supposed to be positive or negative. And it also helps the count if one of your points is negative, because then you don't accidentally not subtract the negative. You know what I mean. Here's how this works. Here's my point 5, 3. How did I do that? 5 over 3 up. I roughed it out. It doesn't matter what, I roughed it out, right? That's the point. Here's 10, 8, about twice as much as 5, and 8's up here. Here's 10, 8. Boom. There it is. Those are my 2 points. I need to find the slope of this line now. 5, 3, that's a little fat for me. I need to find the slope of this line between 5, 3 and 10, 8. And again, I'm doing a little too particular here. Next time I'll do it really fast. How do I do that? I got to say, how much did I rise? How much did I run? Now, is the slope positive? Yeah, it should be positive. I'm going up as I run. I rise as I run to the right. So from 3 to 8, how much did I go up? 5. From 5 to 10, how much did I go over? 5. Your slope is 5 over 5. I got to be careful which 5s I use, which is 1. All right, that gets me there. All right, second one. I'm going to draw this one out first to kind of give you that quick fashion so you can see this one. Find the slope between 12, -7 and 2, -2, and determine whether it is what have you. 12, -7, 2, -2. Let's see. Let's do it like this. So 12, -7 is here. 2, -2 is right here. My slope, notice, will this time be negative. I'll have a negative slope because as I run, it is falling. Okay? It's going down as I run to the right. So we got to figure out, okay, how much, as I run, how much does it fall? So from -2 to -7, I have fallen 5. From 2 to 12, I have run 10. My slope is -5 over 10. This reduces, y'all, to -1/2. That's my slope on this one, -1/2. So again, the drawing still assisted me in finding my answer. I don't have to draw. I can use the formula. I am, of course, going to do that for you next. But see how that drawing helps. See if that makes sense. See if we can get the same answer by doing the alternative. x1, y1, x2, y2. Here we go. Slope is y2 minus y1 over x2 minus x1. -2 plus 7 is 5. 2 minus 12 is -10. And we get there. You must say, Mr. Robinson, you did that one a lot faster. Well, yeah, but I can also calculate these quickly. Can you? Depends. Do I know what I'm doing with it? I do both of them pretty fast. Sometimes I don't draw it. Sometimes I just look at them and do it that way. Anyway, so that's how we're getting those things here. The last slide that I have, this is the last thing, y'all. We're almost done. Slope of the line is determined by rise and fall. Okay, interpreting a slope means describing this change in both y and x in context with its quantity. So just like the intercepts, the numbers here on the graph absolutely matter. All right, we got to find the slope. We got to interpret the slope of this graph right here. Remember that these are rates. These are not values. Okay, I do not care what this point is and what this point is, or point and point. And when I find the slope, by the way, this is drawn out. When I find the rise and the run right here, and I'll just do it this way this time because of time's sake. When I find the rise and the run, these are not just values. These are comparing to one another. There's an important aspect to this. How much do I rise from 10 to 25? How much do I run from 50 to 77? Like that. So my slope is 15 over 27. If I divide these both by 3, that becomes 5 over 9. That's the slope here. Now, we need to interpret it, right? That's the whole point of the slide. We have to interpret the slope. Remember that 5 is the change in y. This is all about y. Delta, the triangle, means change in y. 9 is change in x. This is not a coordinate pair, 9, 5. This means nothing about values. These are not values. These are not values. These are rates. 9 and 5 might not be a coordinate pair here at all. In fact, it's not. It's not a solution to the equation. It's a change. It says every time that I rise 5, I run 9. Every time this thing rises 5, it runs 9. And up 5 over 9, up 5 over 9 like that. Up to 15 over 27, things like that. But we need context. We need context. What is this about? By the way, this is a real world scenario. What is this about? This is about degrees Fahrenheit and degrees Celsius. There is an actual conversion process between degrees Fahrenheit and degrees Celsius. And it has a lot to do with what you see on this graph and what you see in that slope. What I'm going to say is that for every, I'm going to say for every, now what is degrees Celsius? That is y. For every 5 degrees Celsius increase, there is a 9 degrees Fahrenheit. Is that how you spell Fahrenheit? Increase. I'm going to assume it is. It's not. I spelled digress. I spelled degrees wrong with digress, though. Yeah, this is true. Did you know that every time that if you looked at a thermometer and saw that the temperature rose 5 degrees Celsius, say you were looking at something Celsius, say that the temperature outside is 70 degrees Celsius. That's way too hot. Say that the temperature outside. Well, let's see. I'm not going to give you the degrees there because there's more to this. Oh, okay. Here. Let's look at it. Okay, let's look at this. Say that the temperature outside is 10 degrees Celsius. Well, that means it's also 50 degrees Fahrenheit because there's a conversion to it. It's not directly proportional, but there's a conversion here. Now, if the temperature increases 5 degrees Celsius, that means the temperature outside actually increased 9 degrees Fahrenheit. 15 degrees Celsius is also 59 degrees Fahrenheit. That's true. That's true. That's conversion. So every time you see another 5 degrees Celsius increase, there's a 9 degrees increase in Fahrenheit. The other point of this is the intercept. We then ask us to interpret it, but guess what? That point is 32, 0. What does that mean? 32 degrees Fahrenheit is 0 degrees Celsius. That is freezing point of water. That is freezing point of water. So starting at 32 degrees Fahrenheit, or 0 degrees Celsius, every time we increase 5 degrees to 9, stuff like that. There's an equation that can be made for it. There is an equation for it. I'm not going to get into that, but that's the whole idea. All right, so that'll do it for this stuff here. I'm going to go ahead and go back to this last slide again here. Take a look at what we just learned, what some of the target words were. Were we able to do these? I can recognize a linear function symbolically and graphically by looking at the degree of the variable. Remember, degree 1 makes it linear. If it's a degree 2 or absolute value or square root or rational, it's not linear. Yeah, I think we saw that. And on a graph, does it make a line? If so, it's linear. I can graph linear functions by intercepts. Set x and y equal to 0. Find the intercepts, set them equal to 0, and just connect the dots. Yes. Can we interpret the intercepts? State what the points mean with context? Sure. When this is 0, what number is this? What does it mean? And lastly, I can calculate and interpret the slope of the linear function given 2 points. y2 minus y1 over x2 minus x1. Change in y, change in x. Rise over run. As we run to the right, do we rise or fall? There's one thing I didn't mention, and I do want to say it, and it has to do with zero slope and undefined slope. I do want to say these two things. Why is this called a zero slope and an undefined slope? Because a zero slope, what did we say? It has 0 rise and some run. What is 0 divided by something? That is always 0. That makes this have a 0 slope. This one has 0 run. It has some amount of rise, some change in y, but it has 0 run. What is any number divided by 0? That is undefined. That's what makes this an undefined slope, and that's what makes this a 0 slope. Okay. Anyway, so that'll do it for me right here, Mr. Robinson. This ran a little over an hour, but like I said, this was a 3-parter. It was an entire chapter or module of sorts. Hopefully you paused it along the way, you wrote some notes, you understood some of it, you practiced some other problems there. But that'll do it with me here. Hope you understood it all. I hope you had a great Thanksgiving, because I sure did. And hope you're enjoying your leftovers here. And hope you finish off your school year very strongly. All right, signing off.